Hello ELT132, this is Roger Young. In this video we're going to discuss gate enabling. Really this is a pretty straightforward concept, so it's easy to make it complicated, and I don't want to make this complicated for you at all. So that's why we're talking about it. So first, let's do this. We have an AND gate, as you can see. This is an AND gate, and this is a NAND gate. And the only difference is an AND gate, you obviously do not have an inverted output. A NAND gate, it has an inverted output. Okay? So let's just write the truth table here. Let me just draw the gate if I can. It's an AND gate. I just could put AND on top here so everyone understands, right? And this is A. Here's B. And here's Y. That's your output. Generally in this text, Y is the output, okay? So help me here. You should try this at home while I'm doing it. We're going to write the truth table for it right here, right? A, B, and Y, right? Like this. Bring it down. So we start off with 0, right? 0, 0, 1, 0, 0, 1, 1, 1, right? So we have, with 2 inputs, we have 4 unique permutations we can use. So with an AND gate, you know, that would be 0, that would be 0, that would be 0, and this last one, it would be 1, wouldn't it? Because remember, A and B have to be high for the output to be high, right? So there's your truth table right here. Now if you look at this figure in the text, it's figure 2.25. This right here, that's going to be considered to be your control, right? Its control is going to be A. And this signal right here, B, that's going to be your signal. And obviously this is Y is your output. I'm not going to put output, you know, it shows it right here, right? So now look at this first part of this picture here. This is a diagram. It's basically a time type diagram. Time is going this way, right? So the first time, this is broken up into even time. Now you don't know what the time is. It could be a second, could be a tenth of a second, but you know what? It really doesn't matter. It's just saying for this time period, your signal is low, right? For this time period, your signal coming in is high. And then guess what? It's low, high, low, high. And this whole time, your control is low. Now let's look over here at your gate. We're saying that A is low. If A is low, it's going to be one of these cases, isn't it? Because B is 0, it's 0 here, and it's 1 here, right? It doesn't matter what B is. As long as A is 0, your output's what? It's 0, right? And that's what you see. I use the term flatlining, so the gate output is flatlining. There's no change in the output even when you have a signal going in there. So this is inhibited. All right? It's almost like there's a switch there and you opened it. It's not, the signal's not going to go through. Now, what happens when A is changed? Your control changes from a 0 to a 1. Well, now you're going to be in this part of your truth table, aren't you? So when A is 1, which it will be here, when B is 0, your output's 0. Is that right? Here it's 0. Here your output is 0. Right? When B is 1, your output is 1. Well, when B is 1, your output is 1. You see it just oscillates here, 0, 1, 0, 1. This gate is considered to be enabled because the signal is going through. Now let's look at this carefully. This signal that's going through, when it's low, when the signal is low, when the signal is low, your output is low, right? When those are low at the same time and they're high at the same time, they're considered to be in phase, okay? So this particular graph shows them in phase. But this video is on enabled, so I wanted to make sure you understood that when it's enabled, the signal passes through, okay? First point. Now, second point, we have a different graph over here, a different gate, don't we? So the only difference is the output is inverted, isn't it? So instead of rewriting everything, I'm just going to write this. I'm going to draw another column here. I'm going to call it Y bar. And that's pretty straightforward, right? We just put an inverter on the output of an AND gate. We already have the truth table for an AND here. So a NAND is simply going to be the opposite, right? 1, 1, 1, 0. I just inverted these outputs here, right? So let's look what happens. When the gate is 0, your control is 0, right? Your control is 0, it means you're right here in this area right here. Your output is going to be 1 regardless, all right? And notice, regardless of what B is, right? And you notice, what do we have? It's 1 right there. That's considered flatlining. Even though it's high, it's still considered to be inhibited because it's not letting any of the signal pass through it. Okay? Now, here's the next part. The gate enabled. This is when it's enabled. A equals 1. That corresponds to this area right here, doesn't it? When A equals 1, you notice here it oscillates, right? So when B is high, when B is high, Y bar is low, right? So when B is high, Y bar is low. And when B is low, Y bar is high. When B is low, Y bar is high. So you'll notice that this signal, the signal's going on through, however, it's considered to be out of phase because of this fact. When B is high, the output's low. When B is low, the output's high. But regardless if it's out of phase or in phase, this is considered to be enabled because a signal is passing on through it. Another thing to make sure you understand is for a gate to be inhibited, it doesn't matter if the output is high as it is here or if it's low. If it's a 0 or if it's a 1, it doesn't matter as long as it's flatlining. That means that the signal will not go through. The gate is considered to be inhibited. Now, I want to show you something in the presentation. We have another gate here. It's a NOR gate. It's an OR gate with an inverted output, obviously. Just look at this time diagram right here. What do you see? In this case, when A is low, which is your control, right? This is your control. When A is low, you have an output. It's out of phase, isn't it? Because when B is high, the output is low. But you know what? This is enabled. It's not inhibited because it's allowing the signal to pass through. What about over here? This is inhibited, right? Because when A is equal to 1, the signal will not pass through. The output will always be low regardless of what B is, and that's your signal. All right? Let's look at one more. This is an exclusive OR, huh? Now, this should really solidify the concept of gate enabled. This thing always pops up. This is an exclusive OR, right? And notice what happens. When A is 0 and B is 0, your output's 0. That makes sense, right? When A is 0, B is 1, your output's 1. Remember your truth table for 0, 0, and 1, 1, the output's 0, but the other two are high, right? You can check your notes for that. There's no place for me to write that down right here. So this, if you're just looking at the time diagram, this is in phase, and they call it true in this text, right? In phase, it matches the signal exactly. Guess what? It's considered enabled. Now what happens when A goes high? You're still getting a signal out, aren't you? Yes, but this is out of phase. When B is high, Y is low. When B is low, Y is high. So, is it considered to be enabled? Absolutely. It's going on through, right? But this is the complement of it, right? Complement means when one is high, the other is low. When one is low, the other is high. True value means they're in phase. This is out of phase. When in phase, in true form, when one is high, your signal's high, Y would be high. When your signal is low, Y would be low. I hope this has explained the concept of enabling a gate and inhibiting a gate. This was also done in your lab, and I know you've had a lot of practice in it this week. So if you have any questions, please let me know, and thank you for watching.